Welcome back! In this lecture, we'll first shuffle our data and then create the validation dataset. Shuffling is a little trick we like to apply in the pre-processing stage. When shuffling, we are basically keeping the same information but in a different order. It's possible that the targets are stored in ascending order, resulting in the first X batches having only 0 targets, and the other batches having only 1 as a target. Since we'll be batching, we'd better shuffle the data. It should be as randomly spread as possible so that batching works as intended. Let me give you an unrelated example. Imagine the data is ordered and we have 10 batches. Each batch contains only a given digit. So the first batch has only zeros, the second only ones, the third only twos, etc. This will confuse the stochastic gradient descent algorithm because each batch is homogeneous inside it, but completely different from all other batches, causing the loss to differ greatly. In other words, we want the data shuffled. Okay, we should start by defining a buffer size to, say, 10,000. This buffer size parameter is used in cases when we are dealing with enormous datasets. In such cases, we can't shuffle the whole dataset in one go because we can't possibly fit it all in the memory of the computer. So instead, we must instruct TensorFlow to take samples 10,000 at a time, shuffle them, and then take the next 10,000. Logically, if we set the buffer size to 20,000, it will take 20,000 samples at once. Note that if the buffer size is equal to 1, no shuffling will actually happen. So if the buffer size is equal or bigger than the total number of samples, shuffling will take place at once and shuffle them uniformly. Finally, if we have a buffer size that's between 1 and the total sample size, we'll be optimizing the computational power of our computer. All right, time to do the shuffle. Luckily for us, there is a shuffle method readily available, and we just need to specify the buffer size. Let shuffle train and validation data be equal to scale train and validation data dot shuffle with the buffer size as an argument. And that's it. Once we have scaled and shuffled the data, we can proceed to actually extracting the train and validation datasets. Our validation data will be equal to 10% of the training set, which we have already calculated and stored in num validation samples. We can use the method take to extract that many samples. So validation data equals shuffle train and validation data take number of validation samples. Good! We have successfully created a validation dataset. In the same way, we can create the train data by extracting all elements but the first X validation samples. An appropriate method here is skip. So, train data equals shuffle train and validation data, skip num validation samples. Okay, so far so good. We will be using mini-batch gradient descent to train our model. As we explained before, this is the most efficient way to perform deep learning, as the trade-off between accuracy and speed is optimal. To do that, we must set a batch size and prepare our data for batching. Just a quick memory refresh, a batch size of 1 equals the stochastic gradient descent, while a batch size equal to the number of samples equals the gradient descent we've seen until now. So, we want a number relatively small with regard to the dataset, but reasonably high, so it would allow us to preserve the underlying dependencies. I'll set the batch size to 100. That's yet another hyperparameter that you may play with when you fine-tune the algorithm. There is a method batch we can use on the dataset to combine its consecutive elements into batches. Let's start with the train data we just created. I'll simply overwrite it as there is no need to preserve a version of this dataset that is not batched. So, train data equals train data, batch, and in brackets, we specify the batch size variable. And that's all. This will add a new column to our tensor that would indicate to the model how many samples it should take in each batch. Great! What about the validation data? Well, since we won't be back-propagating on the validation data, but only forward-propagating, we don't really need to batch. Remember that batching was useful in updating weights only once per batch, which is like 100 samples, rather than at every sample, hence reducing noise in the training updates. So, whenever we validate or test, we simply forward propagate once. When batching, we usually find the average loss and average accuracy. During validation and testing, we want the exact values. Therefore, we should take all the data at once. Moreover, when forward propagating, we don't use that much computational power, so it's not expensive to calculate the exact values. However, the model expects our validation set in batch form too. That's why we should overwrite validation data with validation data.batch. Here, we'll have a single batch with a batch size equal to the total number of validation samples, or num validation samples. In this way, we'll create a new column in our tensor, indicating that the model should take the whole validation dataset at once when it utilizes it. Okay, great! To handle our test data, we don't need to batch it either. We'll take the same approach we used with the validation set. This time, though, you'll have the chance to do it on your own for homework. Alright. Finally, our validation data must have the same shape and object properties as the train and test data. The MNIST data is iterable and in two-tuple format as we set the argument as supervised to true. Therefore, we must extract and convert the validation inputs and targets appropriately. Let's store them in validation inputs and validation targets and set them to be equal to next brackets iter brackets validation data. Iter is the Pythonic syntax for making the validation data an iterator. By default, that will make the dataset iterable, but will not load any data. Next loads the next batch. Since there is only one batch, it will load the inputs and the targets. Thanks for watching.